The great thing about coming to a trade fair like Electronica is to learn about all the exciting innovation that's been going on. I'm going to talk to Henrik about the new FFT-based real-time microcontroller, which is targeting arc detection in solar inverters. Hi Henrik, it's great to see you here at Electronica 2024. We're at the Texas Instruments stand, and one of the really big topics of our generation at the minute is energy generation, doing it in a renewable fashion, and solar panels are a big part of that. What I've noticed here is you've got something very, very specific in solar energy generation, which is arc detection. Can you tell us a little bit about why that's an important part of a solar system?
Yeah, sure. So, arc detectors has been around in solar for quite some time, and actually in a lot of markets it's required to have it, on all rooftop solar installations. There's actually a standard behind it as well, UL 1699B, that regulates a lot of this market. The way to think about it is in a solar inverter, it's a string inverter system. You have a string with high voltage, high current coming down from a set of solar panels that is installed on someone's roof. Now, with that high voltage and high current on that string, if you have connectors or contacts that sits behind those panels, they become they might become corroded, there might be, bad contact between them. Over time, that can generate arcs. Those arcs are actually it's difficult to see them because the solar panels usually cover it.
Yep.
Number one. Number two is that the arcs is also in a DC fashion, which means that any method, any traditional method to detect arcs is also more complicated, because in an AC arc detectors, which very often is referred to as AFCI, so arc fault circuit interrupters. In that fashion, you always have a periodically changing wave. So you have a 50 hertz or a 60 hertz wave. It also means that the arcs are going to come periodically.
Yep.
In a solar inverter system with DC, you have a straight DC line, so it makes it much harder to detect.
Yeah. Excellent. So, and what sort of voltages, just for people who are not in that part of the industry, what sort of voltages and currents are going down those PV lines?
So it's usually 600 volts, maybe up to 10, 15 amps per channel, so to say. So, if we think about that, then we get that into the string inverter, that high voltage current voltage line coming into the string inverter, and what we try to do there is then we try to put a system to measure the arcs, and we do that usually through some kind of current transformer that then look at the current, because an arc is usually going to show up as some kind of broadband noise pattern atop of this DC line in the system. And most traditional systems today, they are built on an FFT method. So you record that arc, you then run an FFT on it, which basically means that you then have frequency bins, and then you spend some time on trying to decide which frequencies do I think is an arc and which frequencies don't think an arc. Now, the challenge you have is that the frequency bands, or where this noise is going to show up, it's changing because the impedance of the panels is changing with the sunlight on the panel, and it also changes because there is a capacitive coupling between the roof and the solar panel.
Right. Okay. Yeah,
so now you have an arc signal that is moving around in frequency. At the same time, you might also have switching power converters like a power optimizer operating on the same line that generates other noise. Mm-hmm. So in this noisy environment, you're then trying to detect an arc. Yeah. So traditional systems today, they are probably able to do this with something around 60 to 70%.
Right. Okay. And of course that's not enough, and if you're getting failures, that means you're sending people out to look for something that's either not there or something that's maybe very difficult to find physically.
Yeah, exactly.
Now I understand here at the show you're displaying a new real-time microcontroller which has got some new features in it which helps with this process. What's the microcontroller that's integrated into your demo?
Yeah, so the microcontroller we use here is a C2000 P55 microcontroller, and the specialty of that is what we call a neural networking processing unit, which is a small co-processor inside there that we can use to accelerate machine learning algorithms or CNN networks, so to say.
Yeah.
And how we use that in this application is, I talked about before how we do an FFT and we do all this binning. So now instead, what we can do is we build a system, we generate a couple of hundreds of arcs, so however many you have, and then you run that through this through your training algorithm. Yeah. And we have a system here where we can generate arcs, we can then label them, and then we can train on that data and deploy it back onto this microcontroller.
Yeah.
And what we achieve by that is, first of all, it's the importance is on latency. So we can drive down the latency of those machine learning algorithms by about 5 to 10x faster.
Wow.
Because of this neural network processing unit that's inside there.
Yeah.
And we still keep power consumption and so on reasonable for those type of applications.
Yeah.
And obviously, because it's an edge node that we're operating on here, we probably don't want to send this data, off to a cloud somewhere and make decisions far away in the cloud. You want to have this very local inside the string inverter and make the decision there.
So we've got a nice real-time microcontroller with a neural processing unit ready to solve this problem, but where exactly does it fit into a PV system? Is this an independent box that's connected somewhere, or can it be integrated into a solar inverter?
There is both solutions on the market today. You can either have this as an add-on box that sits then usually sits outside of the string inverter, so to say, and just uses the same PV line that comes down, and you just route it through this box and then get it into your string inverter. Yeah. But it's also a lot of string inverter manufacturers that actually put it straight inside of their string inverter so that you have it as part of the overall system.
Yeah. Now, as an engineer, I have a good understanding of how you program a microcontroller. That's quite straightforward. Obviously, the neural processing unit, different type of architecture, and also developing the algorithms is a different process. Yeah. How does TI help the customers with that bit?
So there's a couple of different things that we do there. Obviously, first of all, we have a reference design board that we have built, and with that board, we are able to we can record the current, so to say. We can label arcs through that board, and then we can capture that. All on one of those P55 microcontrollers. Yep. And then obviously we offer then a software suite as well, where you can then do the actual training of your models, and then deploy it back onto a microcontroller. Yep. And for that training, we also offer two different options there. So either for customers that wants to do a cloud-based training to send basically send their ARCs data up to a cloud and do the training inside the cloud. Or we also have an offline version for customers that doesn't want to send their ARCs up to the cloud, and then they can do it on their laptops and then deploy it back to in an in-house system, so to say.
Another key starting point is obviously also software libraries, development environment, boards to get people up and running. What can they get from you to get started with arc detection?
So, obviously the P55 exists as our control cards, so those are available now, and then, this base board here is also something that we want to offer, which has the current detectors and so on it, the labeling channel on there, so it makes it very easy for our customers. So basically you would use your string inverter line and then run it through. You can start then record data right away. Yep. And then obviously the software suite you can download from ti.com. You get it up and running on your laptop, and then you use Code Composer Studio as you do with all TI processors to then program your targets, so to say.
Super. Well, Henrik, thank you ever so much for taking us through that. I find it a fascinating application, and I always find it amazing here at Electronica to see whose results solving which problems, and this is a really neat solution for that.
Great, thank you so much.